We've seen in the lectures that Euclidean division works for Gaussian integers. So what we know is that given m and n, which are Gaussian integers, there exist Gaussian integers q and r such that n is equal to qm plus r and the size of r is strictly less than the size of n. So here for a Gaussian integer, recall that the size is a squared plus b squared. So here's the first problem. Find q and r given n equals 15 plus 7i and m equals 3 plus 2i. Okay, so what we'll do is we'll first use division of complex numbers to find a solution that is rational, the rational quotient of this. That will not be a Gaussian integer, but let's just do that and see what happens. So n by m is equal to, well, it's 15 plus 7i divided by 3 plus 2i, and so we know how to do that. That's 15 plus 7i multiplied by 3 minus 2i divided by 3 squared plus 2 squared, which is 13, and that's 15 times 3 is 45, 45 plus 14, 45 plus 14 is 59, 59, and then we have 21i minus 30i, so we get minus 9i by 13. So that's let's see, so 59 by 13 is 4 and 7/13, and this is just minus 9 by 13i. So this q is not going to work for us because we want a q that is a Gaussian integer. So what we'll do is we'll take a Gaussian integer that is really close to this. So the nearest integer to 4 is to 4 and 7/13 is 5. So take q to be 5, and the nearest integer to minus 9 by 13i is minus 9 by 13 is minus 1. So let's take 5 minus I, and so now if we try to write n equals 5 minus I into 3 plus 2i plus r, then we can solve this to get so 5 plus 3i, that's 15 minus plus 2, that's 17, and minus 3i plus, so minus 3i plus 10i, which is 7i. So what we get is r is equal to 2. R is equal to, well, so n is 15 plus 7i, so we get r is equal to minus 2. So what we have is n is equal to q is, now we've taken q to be 5 minus I into 3 plus 2i minus 2. So q equals 5 minus I and r equals minus 2. And indeed we see that the size of r is 4, which is less than the size of 3 plus 2i, which we saw was 13. Now let's see why this always works. So the algorithm for dividing Gaussian integers, finding the integral, quotient and remainder for Gaussian integers is this. You just do the complex division, and then you round off the real and imaginary parts of the quotient to the nearest integer, and you use that as q, and then you multiply that q by m, and you compute r. And the fact is that this r will always have size smaller than m. And why is that the case? So let's just do a little bit of analysis. So n by m is q plus alpha, and we know that the real and imaginary parts of alpha are each less than or equal to half. So what we know is that real part of alpha, this is what is, we are taking q to be the what we get when we take n by m and round off the real and imaginary part to the nearest integer. So real part of alpha is less than or equal to half, and imaginary part of alpha is less than or equal to half. So what we get is alpha, d of alpha is less than or equal to half squared plus half squared, which is equal to 1 by 4 plus 1 by 4, which is half. So d of alpha is less than or equal to half, and now r is taken to be alpha times m. So d of r is going to, because of the multiplicativity of this d function, which just holds for Gaussian integers, d of r turns out to be d of alpha times d of m, which is then less than or equal to half d of m, which is strictly less than d of m. So this is why this method I've described for doing Euclidean division of Gaussian integers actually always works. Okay, let's move on to problem 2. Here's problem 2. So 3 is, we know, a prime number when we look at the ring of integers, but the question is 3 a prime in the Gaussian integers? Okay, maybe you should pause the video and think about this a bit. It's a slightly tricky one, and I'll show you how to solve it in a moment. Okay, so here's the solution. Let's suppose that 3 is not a prime, and try to see if we can find a factorization of it. So suppose not, then we would be able to write 3 is a plus bi times c plus di, where a plus bi and c plus di are Gaussian integers, so a, b, c, d are integers, and also a plus bi and c plus di are not units. So what that means is, for Gaussian integers, the only units are 1, I, minus I, and minus 1. And so basically that means that a squared plus b squared is greater than 1, that is d of a plus bi, and c squared plus d squared is greater than 1. Because if they were equal to 1, then they would be one of 1i, minus 1, and minus I, which are the units. Now let's use the multiplicativity of this norm or absolute value of complex numbers is the squared absolute value. So that's also multiplicative. So we have that 9 is equal to a squared plus b squared times c squared plus d squared. Just taking norms of both sides of this equation and squaring. So now a squared, a, b, c and d are integers. So we must have that a squared plus b squared and c squared plus d squared are integers, and they are integers strictly greater than 1. Therefore, we must have a squared plus b squared is 3, and so is c squared plus d squared. So a squared plus b squared and c squared plus d squared must be equal to 3. But can we write 3 as a sum of two squares? Well, I mean 3 can be written as 3 plus 0, that's certainly not a sum of two squares, or it can be written as 2 plus 1, that's also not a sum of two squares, or 1 plus 2 or 0 plus 3, which are hardly new choices. So what we get is, but since 3 cannot be written as a sum of two squares, such a, b, c, d do not exist. Therefore, 3 is a prime in Zi. 3 is a prime in the integers, it's also an integer in Zi. Let's move on to the next problem, which is similar, but let's ask about 5. Is 5 a prime in Zi? And the solution, well, we'll proceed in exactly the same manner and see what happens. Okay, you can pause the video here and try to do it yourself and see what happens. Otherwise, I'll show you. So here's the solution. Suppose not, so again we'll proceed exactly as follows. So suppose 5 were of the form a plus bi, c plus di, then we would have, as before, we would have a squared plus b squared equal to 5, and that's also c squared plus d squared. Okay, just the same calculation as before, I just changed 3 to 5. But 5, well, 5 can be written as 5 can be written as 5 plus 0, 4 plus 1 and 3 plus 2, and then you can switch the a and b. So but you look at this 4 plus 1, it's a sum of squares. It's 2 squared plus 1 squared. So I can take a equals 2, b equals 1, and so you're getting 5 is equal to 2 plus I, and into what? You easily see that 2 minus I works. And you can also do it another way, which is you can take a equals 1 and b equals 2, and so you'll also get I plus 2 into I. Sorry, that's the same. What I meant to say is 1 plus 2i into 1 minus 2i, and this will also be equal to 5. So here are two factorizations of 5, and these are not units. However, these two factorizations are equivalent in the sense that if you take 2 plus I and multiply it by I, then you will get minus 1. So if you multiply it by, say, minus I perhaps, then you will get 1 plus 2i. So this this prime is a unit multiplied by this prime. So they are associates, and this prime is a unit multiplied by this prime. So in some sense, these two factorizations of 5 into smaller primes are equivalent. Anyway, the answer to our problem is no, 5 is not a prime in Zi. So you can ask this about other prime numbers. When is a prime number in the integers a prime number in the Gaussian integers? Why don't you try to start with what happens to the prime 2 in the integers? Is that a prime in the Gaussian integers? And you'll probably guess by looking at these two. Well, 2 is 1 plus 1, which is a sum of squares. So 2 is not a prime in the Gaussian integers. In fact, what these two problems show you is that a prime number is not a prime in the Gaussian integers if and only if it can be written as a sum of two squares. And if it cannot be written as a sum of two squares, it will be a prime number in the Gaussian integers. And it's a result in number theory that a prime number can be written as a sum of two squares if and only if it is congruent to 1 mod 4. There's a very beautiful discussion of this in Michael Artin's Algebra book. I think you have to look at chapter 11, section 5 of Michael Artin's Algebra book, and you'll find a complete description of which primes in the integers are primes in Gaussian integers, how they decompose, etc. We'll end this problem session by looking at a problem which I had promised we'll discuss later on, and this is the following. Show that the ideal generated by 2 and x in polynomials with integer coefficients is not a principal ideal. We've seen that if we take polynomials with rational coefficients or coefficients in any field, then they form a Euclidean domain. And so every ideal in this ring of polynomials with entries in a field would be a Euclidean domain and hence a principal ideal domain. However, when you take polynomials with integers, then they do not form a principal ideal domain. And the solution is not very difficult. Maybe you can take a few minutes to try it out yourself. If not, you can follow the solution that I'll give you now. So suppose this were a principal ideal. So it would be generated by some polynomial fx for some fx in Zx. So this would again be a polynomial with integer coefficients. What we would have is that then 2 is in the ideal generated by fx. So 2 is equal to fx times gx. So the degree of 2, which is 0, would be the sum of the degrees of f and g. Therefore, f would have to be of degree 0, which means that f would have to be a constant polynomial. Okay. And moreover, f would be equal to 1 or f would be equal to 2 because it would have to divide 2. And now x is going to be equal to fx times hx for some polynomial hx. This implies that so f has coefficient 1, so you cannot have f equal to 2. So this implies that f is equal to 1. Okay, so if this were a principal ideal, it have to be generated by 1. But 1 does not even belong to the polynomial ring generated by 2 and x. Why is that? Because if you take something in this, any element of the ideal generated by 2 and x is of the form 2 times hx plus x times gx for hx gx in zx. And so if you substitute x equals 0, so we'd have that 1 is 2hx plus xgx. Substitute h equals 0, you get 1 is equal to 2h0 plus 0, which would mean that 1 has to be an even number, which is clearly false. So we get a contradiction. So we see that the ideal generated by 2 and x in the ring of polynomials with integer coefficients is not a principal ideal.